Go ahead.
It's an honor to have you here, Professor Milind Tambe. We are the School of Arts, Media, and Engineering, and it's a pleasure to have you over talking about AI for social impact. So Professor Tambe is a professor at Harvard University, runs the Center for Computation, Research in Computation and Society, and is also director of the AI for Social Good initiative at at Google. And it's Dr. Tambe has made enormous impact in the past few years in pushing out AI machine learning techniques into problems of real social need like global health and transportation and conservation and mobility. So these are all very interesting topics that are close to many people's hearts in our school. We always talk about social impact and social good. So we're all really looking forward to hearing you speak. The audience will be a mix of faculty from math, computer science, arts, media, engineering. This is health. Everybody is being invited, and this is a pretty diverse audience for you. So really looking forward to exciting conversation, Professor Tambe. Go ahead.
Thank you. Well, thank you very much for inviting me. I really appreciate that kind introduction. So for the past 15 years, my team and I have focused on advancing AI and multi-agent systems research for social impact, focusing on topics such as public health, conservation, and public safety and security. The key challenge we focus on is how to optimize our limited intervention resources. So let me just jump right into the lessons that we've learned. First, achieving social impact and AI innovation go hand in hand. I'll start with the domain of public health. Here we have a large population to serve, but limited number of public health resources. Concrete example is work we've done in youth experiencing homelessness in Los Angeles. Harnessing the social networks of these youth, we are able to show that our social network algorithms are far more effective in reducing HIV risk behaviors compared to traditional approaches. But this impact also required advances in social network influence maximization algorithms and bandit algorithms. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. Concrete example is work we've done in Uganda and Cambodia. We're harnessing past poaching data. We are able to predict where poachers set traps or snares, and for the past several years have been able to remove thousands, if not tens of thousands of these snares. But this required us to have advances in what we call green security games, which combines machine learning and game theory. In the past, we've also, in the area of public safety and security, provided a new model called Stackelberg security games and contributed new algorithms that have been in use by security agencies in the United States, such as the Federal Air Marshals, the US Coast Guard, and others. Today's talk will focus on public health and conservation. Now, these areas may seem very diverse, but they're all tied together. That the underlying research area from a computer science perspective is really multi-agent systems. The second lesson here is all of this work is in partnership with communities, nonprofits, and government organizations. Here's logos of some of the community organizations that we've worked with. And our ultimate goal really is to empower these nonprofits to use AI tools and avoid being gatekeepers to AI technology for social impact. The third lesson is that we are interested in the entire data to deployment pipeline and not just in improving algorithms. We begin by immersing ourselves in the domains, trying to understand the kind of problems that are faced by the nonprofit, the kind of data that are available. Following that, a predictive model, a machine learning model, make predictions on which of the cases faced by the nonprofit are high risk versus low risk. And following that, because we cannot intervene on all of the high risk cases given limited resources, we have this prescriptive algorithm, multi-agent systems reasoning intervention, that tells us which cases to actually intervene on. And following that, field testing and deployment is crucial because social impact itself is a key objective of our work. So with that introduction, I'm going to jump into the first topic, which is public health, looking at social networks. I'll cover papers here in my talk from 2017 to now in AI conferences and highlight the role of the PhD student or the postdoc who led that work by putting up their picture in the top right-hand corner. So the first topic I'll look at is HIV prevention amongst youth experiencing homelessness in Los Angeles. There are 6,000 youth who sleep on the streets of Los Angeles every night. The rates of HIV among this population are 10 times the rates of the normal house population. So youth homeless shelters or drop-in centers will try to spread information about HIV reduction by selecting a key set of peer leaders, educate them about HIV prevention, expect them to talk to their friends, and in this way, information to spread in a social network. This is face-to-face interaction and information spreading via this face-to-face interaction. So from a computer science perspective, we have been given a social network graph. So each number here refers to a youth experiencing homelessness. A red line represents a friendship between two nodes, between two youth. And we have to select some number of youth, in this case, 3. And now our social work colleagues will educate them about HIV reduction. And the goal here is to select these nodes in such a way that we maximize the expected number of influence nodes. So influence spreads because if we select a node C, we expect that there is a certain probability, 0.4 here, that the adjacent node D will be informed about HIV prevention. And as a result, an adjacent node E will also be informed about HIV prevention, and that these probabilities are given to us. Now, in reality, there are, however, some challenges we face. In fact, this key lesson here is that lack of data and uncertainty is a key feature of AI for social impact. And so the 3 challenges I'll refer to with respect to applying standard influence maximization algorithms from computer science to our domain are all due to this lack of data. So for example, the propagation probability I mentioned is not known with certainty. We have limited capacity to invite all of the youth. And so it turns out that we need a multi-step dynamic policy. We invite a few youth, some of them may be no-shows, then we have to invite the next set of youth and so forth. And third, the social network itself, which is supposed to be given to us as an input, is often unknown. All we have is a limited query budget. So we can sample from the network by questioning, querying a few youth to understand their local network. And just based on that, we have to solve this problem of figuring out which youth to invite as influencers. So I'm going to sketch some ways that we solve these problems. I'm not going to get into too much details here. So let's go to the first problem. I said that standard influence maximization algorithms assume that you're given a probability, let's say 0.4, that if a youth C is informed, their adjacent youth D, their friend, would be informed with a known probability 0.4. But in reality, immersion in this domain clearly showed that this is very difficult to obtain. So we have uncertainty as to what is that probability of propagation of information. So we can say we sample this from some distribution. And in fact, the mean of this distribution itself is unknown. It lies within some kind of a interval. And so now we have this problem of robust influence maximization. We want to achieve influence maximization despite this uncertainty over propagation probability. We solve this problem as a zero-sum game against nature. So our algorithm is trying to choose peer leaders in a way to maximize influence, but nature is trying to choose parameter settings, meaning the mean of the distribution and so forth, in such a way to cause our algorithm to perform as worse as possible. So we are trying to maximize payoff. Nature is trying to minimize payoff. So we're doing this max-min strategy, where the payoff is the ratio of outcome given our policy to the optimal possible had we known nature's game plan, nature's parameter settings ahead of time. So this is a game that we are trying to solve. If you imagine us as influencers, we are trying to choose these policies of who's going to be our peer leaders. If there's a network of 400 nodes and we have 40 peer leaders to choose, that's 400 choose 40 different policies we could choose from. Nature is trying to choose parameter settings from a continuous interval. So nature also has a very, very large number of strategies to play. So this is a massive scale game, and let alone solving it, trying to represent it in memory is difficult. So how do we solve these games? So essentially, we initialize these games with a small number of initial randomly chosen strategies. And then it turns out there's this double oracle algorithm whereby we keep adding new strategies on the influencer side and nature side, slowly growing the game. These are supposed to be these best responses. And the game continues to grow. And in this iterative fashion, we can solve this game and yet prove often without expanding the whole game, with only expansion of a small portion of the game, we can show that we converge with approximation guarantees. The point being that we can efficiently solve for finding the right influencers despite uncertainty in the propagation probability. I'm going to next focus on sampling the social network. Normally, we would assume in influence maximization that the entire social network is given to us as input. But you can imagine, how would we obtain a social network of youth experiencing homelessness? We would send our social work colleagues to go sit in the homeless shelter and check for each youth, who are they talking to, who are their connections. This is extremely costly and difficult. This is not going to work if you want to take this technique to different cities. Instead, if we can query some small fraction of the youth, 15%, by asking who are your top 5 friends or something like that, and then use that sample to figure out who are the top influencers, that's what we want. So we're going to query 15% of the youth and then choose K peer leaders just from that sample of the graph, such that the performance of our total spread of influence is similar to the optimal possible, had we known the entire social network in advance. So the key idea here is really figuring out how to sample the network. And we have an algorithm that samples nodes randomly, estimates sizes of communities the nodes belong to, and chooses seeds from largest K communities. We can prove some properties of this algorithm, but I'm going to skip that in the interest of time and come to the system that we developed. It's called Change. It combines the network sampling, so it doesn't know the full social network. It's going to do a robust policy generation to deal with all the uncertainty. And it is going to tell our social work colleagues who are the peer leaders, and based on who shows up and who doesn't, say who are the next set of peer leaders and so forth. So now we did a 750 youth study. This is work done jointly with Professor Eric Rice in the School of Social Work at USC. And in this study, there were 3 arms: Change, which is our algorithm; Degree Centrality, which is relying on the most popular youth to spread information; and Control Group, where there's no intervention at all. 250 youth were selected in each of the 3 arms. With Change, the influencers in those 250 were selected using the particular way Change works, of figuring out who are the right set of peer leaders, using the game solving that I mentioned and so forth. Degree Centrality just takes the nodes with the highest degree, most popular youth. And the exact same number of youth are selected in both cases, and Control, as I said, doesn't select anybody. And then our social work colleagues educate these youth about HIV prevention. And then we want to see, was there an actual reduction in HIV risk behaviors at the end of 1 month and at the end of 3 months? And here's what we find. So as far as we know, this is the first large-scale application of influence maximization for public health. And this is done in collaboration with our nonprofit partners, so My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. So at the end of 1 month of this study, if we look at reduction in condomless anal sex, which is one of the HIV risk behaviors, we see that the Change population, there's more than 30% reduction in this behavior, but with Degree Centrality and Control, there was no change, no reduction. Whereas at the end of 3 months, we start seeing Degree Centrality begins to catch up, but the reduction from Change is still higher. The point being that having this reduction in behavior happen faster, as done with our Change algorithm, is important because it is an HIV risk behavior. And also, this is a population where people come and go, and therefore having this behavior change happen faster is important. We also looked at other behaviors, reduction in condomless vaginal sex, and again, we can see that with Change, there's a higher reduction compared to Degree Centrality or Control groups. Or our collaborators who were pleased with this result.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it could really help out a lot of youth.
I wanted to point out some next steps, whereas we have achieved some progress, there's a lot more to do. For example, achieving fairness in influence maximization. Sometimes in some networks, influence, if we use the kind of algorithm I mentioned, there can be disparity in who gets the influence in terms of race, the different racial groups. So in recent work, we've been trying to handle this challenge of fairness. So max-min fairness, for example, maximizes the minimum utility of any community. There's other approaches such as diversity constraints. More recently, we have looked at an approach that essentially gives the policymaker control over how much to emphasize fairness versus performance. Another area of future work, very exciting, is reinforcement learning. So our network sampling algorithm that we presented in the AAAI conference in 2018, and I provided performance guarantees over that in that slide. If we use RL instead, reinforcement learning, to do the same kind of network sampling, we can achieve superior performance in different classes of network families. Similarly, if we use reinforcement learning, then we can achieve significant runtime speed up over change without actually sacrificing performance. So here I'm showing you this RL for IM, reinforcement learning for influence maximization, shown in gray, and orange is change. And we can see that the amount of influence in simulation is roughly equal between the two approaches. However, the reinforcement learning approach, because it's trained on a different set of networks and now it's being applied at real time to a new network, it runs in negligible time, whereas change requires a significant runtime each time. So these are very interesting new directions. We're very excited by them. Testing them in the field would be very exciting new steps. And just wanted to invite people to explore these areas. I'm going to switch over and talk about a different challenge in area of public health. And this is motivating this problem model of restless bandits. And I'm going to turn to maternal and child care in India. This was work done as part of Google Research India. So in India, the situation is difficult. A woman dies in childbirth every 15 minutes. 4 out of 10 children are too thin or short. And we are very fortunate to be working with a nonprofit called Arman, which serves 25 million women in India. One of their programs is called M-Mitra. It's a weekly 3-minute automated voice message to a new or expecting mother. It may be a message of the form, you are 3 months into pregnancy, you should use this health supplement. Or your baby is 3 months old, enroll them in this government program. 140 such voice messages in the local language, in the voice of the local health worker, are delivered to these mothers. And they're shown in randomized control trials that women who listen to these messages are significant benefits in terms of their health and the health of the babies. 2.2 million women have enrolled in M-Mitra. The challenge, unfortunately, is that significant fraction of women who enroll, eventually 30 to 40% even, may become low listeners. They stop listening to messages. Arman has limited intervention resources. They can issue service calls to a small number of beneficiaries to ensure that they don't drop out, that they keep listening to these messages. So the question for us in terms of, consider this example, you have a large number of beneficiaries, 50,000, and you can place 1,000 service calls per week. Which 1,000 would you select? Which 1,000 beneficiaries, mothers, would you select to make these service calls to? So that ultimately the total number of health messages that are being listened to gets maximized. So think about a health worker. I'm going to not use 50,000, but use 5 here. There are 5 mothers in her care. 4 of them have not listened to a voice message from Arman in the last week. 1 of them has, shown in green. And she has to choose 2 only that she could do a service call to get them to start listening to these messages. So she chooses, suppose, the first 2. This turned out to be a good choice. Those 2 started listening, and there's a third one who automatically converted to listening. Now she has these 2 who remain red. They're not listening. So she has to decide next week which 2 to call. So she may say, okay, I'm going to call these 2 who are in red. Unfortunately, this was a bad choice. Not only these 2 red did not convert to green, but it turns out that our original 2 also have stopped listening. So this was not a good choice of who to place service call to. So we have this challenge that a service call may not change beneficiary state. Beneficiaries may change their state on their own, and yet we have to prioritize 1,000 beneficiaries per week. We solve this problem by modeling it as a restless bandit, where we can choose k out of n arms per week. For those who may not be familiar with restless bandit, each mother, each beneficiary here is modeled as being in one of 2 states. A bad state, she was not listening to a message. A good state, she listened to a message in the last week. And we can take actions of doing a service call or not. And as a result, there is a transition probability of going from bad state to good state. A service call increases the probability of transitioning from a bad state to a good state. Not making a service call means a higher probability of remaining in a bad state. And now we have 50,000, or in Arman's case, ultimately 300,000 such women who are enrolled at a time. And so that means there's 300,000 such arms, each mother modeled via these states as shown. And then the normal way of solving a restless bandit is to compute something called a Whittle index, which I'm going to skip over, and choose the top 1,000 arms based on their Whittle indices. So this is the state of the art. The problem, of course, is that the transition probabilities are not actually given to us ahead of time. So we are going to infer them based on available data. So we have some data about women and whether they listen, based on service call, did they change their listening behavior or not? And so we can cluster this data and then map features to clusters. That means that when a new beneficiary comes in a new time step, at the testing step, we can, given her features, age, education, etc., figure out what is her transition probability of going from a good state to bad state and so forth. And having done that, now we can compute Whittle indices and choose the top k women to call. So we recently completed a very exciting 23,000 beneficiary field study. This is the first large-scale application, as far as we know, of restless multi-armed bandits for public health. And so here, we again had 3 groups: a restless bandit group, a round-robin group, and a current standard of care group. In each group, we had 7,667 beneficiaries. We called 225 of these beneficiaries in each group per week for 7 weeks. In the restless bandit group, the RMAP group, the 225 were chosen according to their Whittle index based on our approach of computing transition probabilities and so on. In the round robin group, they were just sequentially selected, one group, then the next group, then the next group, and so forth. There was no strategy other than just sequentially calling people. And current standard of care, there is no service call being made. And our question now is, how many more health messages were listened to in the RMAB or the round robin group over the current standard of care group? And here's what we find in the 7 weeks. On the x-axis are different weeks, up to 7 weeks. On the y-axis are how many more messages are being listened to over the current standard of care group. What we find is that the restless bandit group, there is more than 600 more messages being listened to. With the round robin group, there's very little improvement over the current standard of care group. If we look at it in terms of statistical significance, we see that we achieve statistical significance of the restless bandit group over the current standard of care group but not in the round robin group of our current standard of care group. The point being that if you are going to have a nonprofit trying to make service calls to retain beneficiaries in the program, optimizing this service calls is important. If you just call people randomly or sequentially, you will not achieve any statistically significant improvement here as shown over not calling at all. So this has been very encouraging. We have launched a new 100,000 beneficiary study with the ultimate goal of transitioning our software to Arman. Once again, just like in the previous case, there are many exciting new areas of work. Tuberculosis prevention, which is another big disease in India, for example, is one where again restless bandits can apply. So, for example, a patient has to take pills for 6 months. And now, again, you can imagine a health worker who has a number of beneficiaries in her care trying to remind these patients to take their pills. And so you can imagine that in this case, she may have some 3 patients she could call per week or per day. And she may say, okay, I'm going to call these 3 patients. The difference compared to the previous application here is that the state of the patient is not known. We don't know if they took their medicine last night or not. And so when we call them is when we find out, oh, these 2 patients didn't take their medicine last night, but they took their medicine. The third one did not take their medicine. And now based on this, now you have to choose the next 3 patients to call and so on. It's a problem similar to the one we just saw with restless bandits, except that the state of the patients is not known. So this is this challenge of partial observability. And so we have a NeurIPS paper last year that addressed this problem. So when an arm is not played, a patient is not called, that is, we don't get any observation. And all we can do is update our belief state about that patient, meaning a belief that the patient is adhering to taking this medicine is going to drop. If, however, we call the patient, uncertainty collapses. The patient may say, I took my medicine last night. That means, state is green. They took their medicine. Or state is red. They say, I didn't take my medicine. So this collapse of uncertainty leads us to this specialization of restless bandits that we've called collapsing bandits. And because of that, we can develop a fast algorithm. For those interested in optimality of this algorithm and so on, we have some theorems that look at indexability. I'm going to skip those. In simulation, we can show here that our algorithm shown in blue is much faster than orange, which is the state of the art, without losing much in solution quality. There are many other exciting challenges here in terms of a lot of work in restless bandits, including the work I've shown, often assumes 2 states, good and bad, 2 actions intervene or not. What if we can have multiple states and multiple actions? Or if our goal is to achieve some kind of risk-averse objective, or we want to learn policies via Q-learning. So these are all very exciting areas. It's a very interesting area for future work. I'm going to close this section on public health by talking about some recent work on COVID-19 agent-based modeling. We've been conducting this work using agent-based simulation models for understanding COVID-19 testing strategies and so forth. I'm going to just talk very briefly about our paper in Science Advances that often gets referenced, like last week in this opinion piece in New York Times. And so this is the one that looks at accuracy versus ease in COVID testing policy. This is joint work with our colleague in the Harvard Chan School of Public Health, Professor Michael Mina. And the question he posed us was to model this problem of, should we be using RT-PCR tests, which detect very low viral concentration, but are expensive and take time to get results back, versus this rapid test, this less sensitive, which requires higher viral concentration, but is cheap, and you get test results back in 15 minutes, as you may have seen in home tests that you may have done. And so if you're Harvard and you're trying to figure out which test should I run in order to screen my population, should I be using this PCR test or this antigen strip? So we did this modeling for Michael. So if we look at testing everybody in our population, student population, faculty population, every 3 days using PCR of this antigen strip, and assume that anytime anybody is found to be positive, we quarantine them. If we can run these tests at the same frequency and we get results back instantaneously, then the PCR test is definitely better. This is shown in blue, it is lower. Lower is better here. However, on the y-axis is the total number of infections. However, as we said, PCR tests, the more sensitive tests, may take a little longer. And just this 1 day delay in if there's only a 1 day delay in getting back results, then the advantage of this more sensitive test is lost. There's more infections because there's a 1 day delay in isolating infected people. If, because of cost, we cannot run the PCR test with equal frequency, we run it every 5 days, whereas the antigen strip test we can run every 3 days. Again, the advantage of having a more sensitive test is lost. The point being that rapid turnaround time and frequency is more critical than sensitivity for COVID-19 surveillance. That was the paper for Science Advances. It has received widespread coverage in the news media. We were thrilled one day when Dr. Fauci talked about our paper. And recently, we see that in President Biden's plan, there is this emphasis on rapid tests. Now, we credit entirely Michael Mina. We just were glad that we could play some role in modeling, in helping him push this agenda forward. So in the last roughly 10 minutes or so, 10, 12 minutes, I wanted to discuss a little bit of our work on conservation and then open it up for questions. So in national parks around the world, such as in the Queen Elizabeth National Park in Uganda, there's wonderful wildlife, but there are threats to wildlife, snares or traps that get placed by the thousands to maim and kill wildlife. Rangers search these parks to try to locate these snares. Our goal is to figure out how to help these rangers figure out where the snares are. So given this large park, we divide it up into 1 kilometer by 1 kilometer grid square, and we're trying to predict where rangers should go to find these snares. So we have past poaching data. So we have for each grid square, ranger patrol frequency, we have animal density, distance to rivers, roads, and villages, and so forth. And we are trying to predict the probability of finding a snare in that 1 kilometer grid square. And so I'm going to skip over the details of the model, machine learning model we built, and I'll come to the first test we did in the field. This was the first pilot in Queen Elizabeth National Park. Doing the tests for the paper and showing training set, test set was not convincing for our partners in the field. So we selected these 2 9 square kilometer areas shown in green here, the dots we asked these rangers to patrol. And you can see that the red dots are where previously snares are found. So we're not asking rangers just go back to the place where there are more snares found. We're asking them in this case to new infrequently patrol areas. That was the test, find new areas. And now we are asking them to go there, and we told them you're going to find snares. Now, this just happened to be before a month before a conference deadline. That meant that if the rangers were going to be able to find snares, we would be able to write a paper. If not, there wouldn't be any paper. So the rangers would patrol and then send an email. What happened today? What happened today? And so forth. Initially, there was no result. And then they said they found a poached elephant with its tusks cut off. This was a sad event, but at least the machine learning system was pointing us in the right direction. And then a whole elephant snare roll was found and removed. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove this elephant snare roll, thus potentially protecting the lives of many elephants. Again, these are areas that were not being patrolled earlier. So this was seen as a great validation. And then we found 10 antelope snares and so on. So after that, we did a larger scale test in 3 national parks, Queen Elizabeth, Murchison Falls in Uganda, and Sri Park Wildlife Sanctuary in Cambodia, where we selected 24 areas. And for each area, we predicted with a high risk, meaning more snares would be found, or low risk, meaning less snares would be found. What we're guarding against here is that these are all less infrequently patrolled areas. We are trying to show that our machine learning system is not only calling any infrequently patrolled area as, oh, you're going to find snares there, but it is being discriminatory. It's able to discriminate between high risk, where more snares would be found, and low risk, where less snares would be found. Of course, the rangers didn't know what our machine learning system had done. And then we asked them to go patrol and then tell us what happened. And what we find is where we predicted high risk, more snares were found. Where we predicted low risk, less snares were found. And this happened in all three parks. In Sri Park Wildlife Sanctuary, from 2018 to 2019, when our system called PAWS was deployed, the number of snare captures jumped fivefold. These are pictures from the actual capture of snares in Sri Park Wildlife Sanctuary. And just in March of 2021, for example, 1,000 snares were found with the help of PAWS. So given all this evidence that has accumulated in favor of PAWS, PAWS is now being made available to the SMART platform. This is what gets used by these conservation agencies worldwide. So we've made this software available. Rangers can download and start using it. A lot of testing is going on. This very exciting time in terms of deploying the system worldwide so that we can assist rangers in the dangerous tasks that they do. I wanted to close again by two new directions to pursue. One of them has been integrating real-time information. So this was work that we did with a nonprofit called Air Shepherd, which flies drones in South Africa, and then does infrared, flies with infrared so that it detects humans. But this is all, you can see it's very hard to see these humans as white hot dots in a forest. And so we've built a CNN-based system to automatically detect wildlife and humans. Having built the system, we delivered it to Air Shepherd, and now we built an additional system for using game theory for optimal deceptive signaling. The idea goes something like this. If you imagine there's a set of poachers, and now we have this drone that's flying overhead. There's a small chance, 0.3 probability, that when the drone is flying overhead, there is a nearby ranger, because we don't have rangers everywhere. Very likely 0.7 chance there is no ranger nearby to stop these poachers. So we've detected these poachers using our drones, but we can't stop them. What do we do? So Air Shepherd has this idea of flashing lights at the poachers in order to send a signal that rangers are on their way. But if you send a deceptive signal every time, that when there are no rangers, you start flashing, the poachers know that this is really a fake signal and they will stop believing it. So we have to be strategic in our deception. And so that means that sometimes when you have a ranger nearby, you may still show this deceptive signal. And the key idea then is to balance the probability of how many times you show the signal when a ranger is nearby and when the ranger is not nearby, such that from a poacher's perspective, they know that this is a deceptive signal, but it's still in their best interest to run away when they see the signal, because if the probabilities are matched in such a way that they can't know for sure whether there is a ranger nearby or not. And so this has been some work that we've been pursuing. Another area of work is data scarce part. So the kind of work I mentioned, there's a lot of data, like in Sri Park Wildlife Sanctuary. So we can make good predictions about where poaching is happening. But there are many parks where there's very limited amount of data. So you can't quite run the machine learning models. So on the one hand, you want to do patrols to collect more data of poaching, but you also want to detect illegal activity simultaneously. So you want exploration and exploitation happening simultaneously. We can model this problem as a multi-armed bandit. And so here we have these different targets with features, and poachers are going to be setting traps. And we want to, given a budget B, like rangers can patrol 5 kilometers a day. How do we distribute the ranger effort among the different targets so that we maximize, that we reduce the regret with respect to the optimal possible? And so we have an algorithm called Lizard that was presented at AAAI 21, and we can prove some new regret guarantees. I know I'm about at the 40 minutes, so let me close by outlining some of the lessons that we've learned. First, achieving social impact and AI innovation go hand in hand. Second, our goal here is to empower nonprofits to use AI tools and avoid being gatekeepers to AI technology for social impact. Third, in AI for social impact, it is important to focus on the entire data to deployment pipeline. It is not just about improving algorithms. We actually want to achieve social impact in the field. It is important to step out of the lab and into the field. That's how a lot of problems get uncovered. Important to embrace interdisciplinary research. It seems like in your school, that's exactly what you're doing. But it's important for us to go and talk to social workers, work with conservation scientists and others. And finally, a lack of data is the norm. It's a feature in AI for social good. We can't throw up our hand and say, well, there's no data, I can't do anything about it. It has to be part of the project strategy. So with that, I'm going to close. And if you wanted to follow the work that we've been doing, I often post our latest papers on my Twitter feed. Thank you very much for listening, and I'm very happy to take any questions that you may have. Thank you.
So thank you so much, Professor Tambe, for an inspiring talk. I think you hit upon almost all the key, theme areas that excite our students and our faculty. We have a lot of students here on the call. We have several faculty who are probably excited to ask questions. Lack of data, putting models into the real world, dealing with the socioeconomic and political factors around putting even simple things out in the world. All these things are, our aspirations as well. Let me start with opening up the, stage for questions from the audience before I ask anything. Hi, folks. Any questions?
Hello.
Yeah.
Okay.
Go ahead.
Okay.
Go ahead and first introduce yourself and with your name, and then go ahead with the question.
Okay. So I'm Hongjun. I'm a first-year PhD student working with Pavan in Geometric Media Lab.
Great.
So yeah, honestly, I mean, I'm not fully understanding in detail things, but it seems so what you're doing, you're presenting today is really interesting to me. So actually, the moment that I decided to go to graduate school, I wanted to do something helping public health for people, those who are in struggling poverty or disease like that. So yeah, that being said, all of the work, what you've done in the past looks more trying to solve the real world problem. Sounds like more practical. So yeah, I don't have a technical question for now, but I have one silly question. So yeah, probably no one's gonna ask this. So what most memorable moment or experience have you had in the past while you are doing all these kinds of great work? That's my question.
That's a very nice question.
Yeah.
So I think, I was doing work pretty much in the lab. I mean, it's important to do sort of algorithmic work. That's what I was doing until around 2005, 2006. And it was in 2007 that I decided to switch to working on AI for social good or AI for social impact full time. And the most memorable moment in that way was meeting with this chief of airport police at Los Angeles named Errol Southers. He's a very inspiring individual. He was the first nominee that President Obama had as the head of the TSA. And it was, sitting in his office, he was asking me how could we improve security at the Los Angeles airport, and we developed a system called Armor that we delivered to them that has been in use since 2007 for 10 years to try to improve their security. And I can get into more details, but going to the memorable moment, it's in that office as he was talking to me that he convinced me that, we have to really, because he was using all kinds of technology to try to improve security and public safety. Yeah. And so that's when I started getting convinced that really there are important problems that we need to pay attention to. In that case, it was counterterrorism. And that we as AI researchers, as computer scientists, as technologists have things to contribute. And those problems have things to contribute to us in terms of presenting us newer research challenges that we had not thought of before. And so I would say that that's that switch. So that's when I changed. So all my papers changed, all my lab changed, everything changed to starting to work on problems that were much more directly applicable in society.
Yes. Yeah. Thank you very much for your answer. Yeah.
Thank you.
Yeah. Thank you.
There is a great question by Ashish Amresh. Ashish, do you want to unmute yourself and ask?
Yeah, hi, Dr. Tambe, great talk. Really relevant to everything that we are witnessing today in our society all over the world, actually. And so we're very, it was very refreshing, so to say the least, that this is an approach that I think many computer scientists should take. And one of the things I'm wondering, listening to your talk, is can you share some experiences about barriers or things that as researchers, as fellow computer scientists want to move in this direction, follow your lead, so to say. How do we get actual community members to really integrate, into the research and be participating of the work? Because a lot of times it can come across as extremely technical. And there is always resistance to being involved in this kind of work. To say loose, it can be turned too nerdy for most people to be participating. So can you share some strategies, thoughts, ideas on how do we bring folks who may not see us as collaborators to really accept what we do?
A fantastic question. And if you don't mind, let me advertise our Google India program here, which is open to people from around the world. So every year we run a program whereby nonprofits can apply and professors from around the world can apply. And so last year, for example, or this year, essentially, more than 150 faculty members, more than 150 nonprofits applied. And then we run a big matchmaking session. So each professor gets to meet with 3 nonprofits. Every nonprofit gets to meet with 3 professors. And then they write proposals together. And then we do selections, and based on the proposals that were written, and then we fund the faculty member and the nonprofit to work together. And in this case, because the nonprofits are eager to get help, there's not that immediate barrier. So that at least is a very concrete suggestion, I hope, that may be of some use. We will run this program again next year. So I invite you to apply. It's very exciting. I've listened to these conversations between the faculty members, say from University of Oregon, talking to some nonprofit working on diabetes patient in South India, something like that, and them writing an exciting proposal together, coming up with completely new ideas. So that's a very direct suggestion. But you are absolutely right that it is not easy. I don't, to kind of develop these partnerships with nonprofits, and it takes time, and it doesn't always succeed. In some cases, you may find that a nonprofit, I've talked to conservation agencies in some countries where the minister in charge, the top officials are all excited about AI, but you go talk to the rangers and they will say, look, we just need better shoes. We don't need any more technology or anything like that. And so there are places where, certainly AI is not the needed solution. But in other cases, often, having these kinds of conversations over time helps. And for example, my partnership with the World Wildlife Fund, Wildlife Conservation Society, and others, it was just a whole bunch of cold emails being sent to a lot of famous conservation scientists saying, hey, I'm passionate about this. I want to somehow play a role. And can you guide me? And then, through a chain of emails, finally, I got access to someone in Uganda, the Wildlife Conservation Society people in Uganda. And they said, come down to Uganda. We want to show you what we have and collaborate with you. So I flew down to Kampala City. I went to Murchison Falls National Park, and there met with the Wildlife Conservation Society officials, and that's how the collaboration started. So for those who are interested, I guess I'm saying, if you are interested, apply to our Google Research India program. But otherwise, there are many strategies. You could cold email. Another strategy we have used in our center at Harvard is we've invited a whole bunch of nonprofits to come and present their work, and then try to have faculty members meet with these nonprofits and launch projects that way. So hopefully some of these ideas may be of use in terms of launching new projects.
Ira Bennett may have a question. Ira, do you want to unmute yourself?
Sure. Yeah, I'm here. Thank you so much, Professor Tambe, and thanks, Pavan. So I think my question is actually the opposite of Ashish's, which is very often the work that nonprofits and community organizations and even local governments need isn't on the cutting edge of what the science is. So how, especially when you're working with junior colleagues, how do you balance the idea for them to show their ability to stay on the cutting edge of scholarship, which is often significantly ahead of the needs of organizations, while also balancing this social good agenda?
That's an awesome question, and it's true that often the problems that come out, they will offer some kind of a very simple problem where you say, I can just use a simple decision tree and it works, and why bother with anything more complex? True. So there is some kind of examination, some kind of investigation that needs to be done in collaboration with these nonprofits, where there's simpler problems. Perhaps those are good fits for students in your class on AI for social impact or something like that. But then there are these other problems, where nonprofits are struggling with much bigger, they have bigger data sets and so forth, and they're really trying to solve these really complex problems. So that may be one way. The other thing sometimes, as you may have noticed, we noticed, is that the nonprofits would come to the table with a certain problem because that's what they think we can do. And once we educate them that we can do so much more, then they say, oh, now there's this other problem that we truly want to solve. So for example, I showed you the work with Arman, where we selected these 1,000 people to call for social, for service calls. But the original problem as posed was, can you predict for us who are at a high risk of drop-off? Which is like, okay, that's not that difficult. But then when we started talking, we realized that yes, we can say, okay, all these 30,000 people are at risk of drop-off. That's not useful to them because they can't call all 30,000. So ultimately, they were going to make a selection of some people to call. Once we understood that, that's when we realized that, it's more complex than just, running a simple prediction algorithm. And there's a lot of complexity. So on the one hand, I entirely agree that it's an art right now. It's a sort of you have to try to sort of talk to these nonprofits and really try to scope out problems that will lead to these interesting AI advances. But on the other hand, sometimes it's actually deeper conversations that lead to these problems. So often, for example, even with Arman, for a year almost, they were just saying, just point us to these high-risk people. And that's what we kept doing. And then it's only when sort of longer conversations. So it's sort of a development of relationships. It's longer conversations. I often tell, my junior colleagues that, they are not going to come to your doorstep and say, here's a nice restless bandit problem. Here's our risk, our objective. And now please solve this problem. And look, here's all these research problems for you to solve. That's not the way it's going to unfold. You have to be patient and things develop over time and so forth. So you may have other answers, but I guess that's the best I can do.
So can I ask a follow-up?
Please.
So
yeah, go ahead.
So how do you then help the junior? You can tell the junior colleagues, you got to be patient, but it takes, that's great advice, but that's not particularly, operationalizable. So,
exactly.
So do you have a program where you sort of basically coach people on how to do this? Because, I do this sort of work, but I came from a chemistry background. It took me a long time to figure that out. And so we try to develop tools. So how do you sort of get people up to speed on that?
No, it's a, so I guess in my lab in particular, there is a stream of partnerships that have been built over time, and newer partnerships are being built. And so the ones that are well developed, where there's a long-standing relationship, where there are problems that are continuously bubbling over, those are the ones that you get people to get on as they want to publish papers and advance science and so forth. And the other ones are ones where there are more senior people in the lab and myself are kind of continually developing those leads to try to get them to a point where the junior people can come in and start attacking them. So that's what we have done.
So sort of a team effort with sort of continual coaching involved. Yeah, I mean that makes obvious sense. It helps that you're a big operation to some degree that it's able to do that.
That's right. No, but it's a very important problem, and I mean I agree with you that there is this issue that so that's why in our matching program for Google Research India, for example, it was important for us to filter out those nonprofits, or those in the matchmaking session, for example, that we ran. Every faculty member met with these multiple nonprofits, and they had to really, talk to them and say, can I really find a research problem that would interest me and allow me to advance something?
So did you do a training program for those? Do they have some sort of training program before you sit them down in front of a nonprofit?
Yes. So there was there was like a lot that happened in order to get people to think through all these issues before they went in. And then we also sat in as experienced AI for social good researchers to kind of coach the conversation to go in the right direction and so on. I mean, there's so much to do. I feel like we need to kind of compile all this knowledge in some kind of a handbook or something of AI for social good, where all these things need to be brought out so that people who jump in don't run into exactly the kind of problems you're mentioning.
I mean, it's beyond AI and social good. It's any kind of technical expertise and social good, right? I mean, this is
agreed.
So yeah, it's a huge problem, and I think there's a lot of people working on it. But I think this was a great example of how you did it. Thank you so much for your presentation.
Oh, thank you for your questions.
So we have time for one last question, and we have Christina who might want to ask a question which is related to what you just ended on. So Christina, go ahead.
Hi, I'm Christina. I serve as Director of Social Embeddedness at ASU. This might seem like a pretty simple, straightforward, or dumb question, but how do you build trust? So you are so incredible at being a champion of this work and communicating and articulating how important all of this is. What are the skills and the resources or the things that we should be doing with our students and our staff and our faculty to kind of help evangelize this as well? I guess those two questions.
No, that's a very important question. And I feel like I need to train my own students in this and my other, group members at Google and so forth, because this is really an important skill. As I mentioned, it has indeed happened that one of my postdocs, we were meeting with a nonprofit. I said, okay, go meet with this nonprofit and then come back and tell me what happened. And his answer was, I went there, I talked to them, but they did not give me a problem to solve. And I was saying, in the first meeting, they're not going to give you here's a nice AI problem, write a paper about it. So I agree that giving training to people to understand that this is a process, this is relationship building, that this will take multiple steps, that they don't quite understand your language, and you don't quite understand their language, and and humility is important. Going in there thinking that I have this magic of AI and I can solve your problem, that's not the attitude that's going to work. That you have to let them, you have to kind of go there, look at their actual context. So if you're thinking about youth experiencing homelessness in Los Angeles, you have to actually go see this drop-in center, see how they're operating, or if it's a wildlife conservation, go to the national park. So these are important things that need to happen. So I guess one of the things that is very important is what we've been informally calling immersion, which is just actually understanding the problem by going to the location, meeting people in their local context, and working with these community-based organization in all of the steps that I showed, the immersion step, the predictive, building a predictive model, building a prescriptive model, testing things in the field. Every one of these steps, that this is not something where, okay, we are going to take your problem, we're going to take your data set, then go to our lab, write a nice paper, and then come back and show you the result, and you better deploy it. But rather that it's a very, something that gets developed in partnership. So I guess if there's one word answer, it would be close partnership to build trust. But it's a complicated process, and you've hit the nail on the head by saying that this is something where we need to develop a good training program, and not just sort of this, ad hoc way that I'm currently perhaps training my students in. And this is so much more beyond AI. It's not just, we're not just sort of training them saying, here's the nice algorithm, but there's all these other things that are going on in order to achieve AI for social impact. Thank you for that question.
Thank you for that answer.
So thank you so much for making time out, and thank you so much, Professor Tambe, for making time out for us. It has been a pleasure and an honor. So we will continue the conversation. I'm sure you will get a ton of email from several people asking advice, and that might include me. So thank you so much, and we have a follow-on call right after this. So
yes, all right.
Thank you so much, everybody. Appreciate your attendance, and feel free to send us
thank you
questions or any other comments. Thank you so much. Yeah.